Pues yo creo que ya, ¿no? Para no hacerlo esperar. We're going to start in a moment.
Okay.
¿Vas a poner una cortinilla o algo? ¿Ya? Okay. Well, first of all, I would like to thank Professor Tom Lubinsky, who accepted to give the colloquium. He's a very, very famous physicist, and I'm going to give Sean some details about his biography. So Professor Lubinsky received his title in physics from the California Institute of Technology, and his PhD. First of all, I would like to thank Professor Tom Lubinsky, who accepted to give the colloquium. He's a very, very famous physicist, and I'm going to give Sean some details. So we have an echo. Yeah, let me try it. Yeah. So he was a National Science Foundation postdoctoral fellow at the University of Paris-Sud in Orsay and a postdoctoral research associate at Browne University. In 1971, he joined the University of Pennsylvania, where he served as the chair of the Department of Physics and Astronomy from 2001 to 2009. He retired in 2017, and he is now the Christopher Browne Distinguished Professor Emeritus of the University of Pennsylvania. Professor Lubinsky's early research deals with thermal critical phenomena, particularly in random systems, in semi-infinite systems, and in liquid crystals, and with geometrical critical phenomena associated with percolation, gelation, and branched polymers. A major focus of his work has been soft materials, especially liquid crystals. He has investigated the interplay between symmetry in dynamical and topological excitations in thermodynamic phases, and he played a major role in collaboration that developed the theory of elasticity, hydrodynamics, and topological defect structure of quasicrystals, and in fact predicted the existence of the twisted grain boundary phase, the liquid crystalline analog of the Abrikosov vortex phases in superconductors. He worked closely with experimentalists on problems in colloidal science, microrheology, and liquid crystals in confined geometries. His more recent research has centered on the elastic and dynamical properties of soft materials, like liquid crystalline elastometers, biopolymer networks, and granular materials. He's currently working on topological mechanics, and he's the co-author of a graduate text on condensed matter physics, which is considered by many as the definitive reference on the soft side of solid state physics. It's a very, very nice textbook. And Dr. Lubinsky is a fellow of the American Physical Society, the American Association of Science. He's a member of the National Academy of Science, the Academy of Art and Science, and honored member of the International Liquid Crystal Society. And he was named as Sloan Fellow and a Guggenheim Fellow. So it's really a pleasure to have Professor Lubinsky, and I would like to thank again that he's here today to give us a talk. Thank you.
Okay, is that passing the word to me now? Okay, thank you very much for that very nice introduction. I'm going to now open this for viewing. Can everybody see properly? Do I get any feedback?
Yeah. Yeah. I can see it. Yeah.
Okay, so I'm going to talk about metamaterials and topological mechanics, mostly what leads up to topological mechanics. The metamaterials part is really to point out that there is a revolution going on in material science now that will allow sort of what we call made-to-order materials, particularly lattices of various kinds, and some of them are really topological in nature. So this is the crew of people who worked with me on this. Xiaoming Mao, my longtime graduate student, who's now getting associate professor in physics at the University of Michigan. Anton Suslov, another student. Olaf Stennel was a postdoc with me for a long time. And, all of the others, including James Clerk Maxwell, who was the giant who's hiding behind all of this. So let's go. So back in 1848, James Clerk Maxwell was interested in the stability of these large new structures that were emerging from the Industrial Revolution. And he posed the question, what are the conditions under which a bridge like this is mechanically stable? And he devised what's, his original view about the stability. Namely, he said these nodes where the struts meet are like points on a lattice, and they have each one d degrees of freedom in the d-dimensional, or in our case, d equals 3-dimensional space. And the struts here provide constraints. If they were totally incompressible, there would be an infinite constraint there. And he said that you have sloppy modes or zero energy modes whenever dn, the total number of degrees of freedom, exceeds the number of constraints. And this particular pattern, which I remember from freshman physics, is one where you can actually get all of the tensions and the forces on the sites by doing a calculation that doesn't involve the microscopic metallic character or character of the material that's acting as the bond between them. So we're going to revisit this in a variation of this theorem that turns out to be very important for all these stability questions. Wait a minute. Why am I not getting? Okay. Where did I go? Why is it so slow?
We
This has
can.
never happened before. What am I being held up by? Okay, there's that. They went down instead of right. Okay, so here's a typical 3D printer. It involves mixing together two different materials and then joining them with some kind of, usually an optical or laser film. And what you do is you build up point by point instead of what happens in these 3D printers are often called I'm having trouble putting that. There's called additive manufacturing, whereas as opposed to the destructive manufacturing, or where you take things out, you use a drill or something to make a hole. Here you join things together and build point by point in an additive fashion. And you can see that the plethora of things that you might make. Some of them are sort of amusing. Some will be useful, like an artificial ear, like that. This shows where things are as of the early 21st century. You can make these objects which have a length scale that's of order 10 microns, as you can see. This one here is particularly interesting. That this is a diamond lattice, and it's constructed so that the struts here are thicker in the middle and thinner at the end. And this gives it a lot of compression strength and a fair amount of flexibility at the node. So this is what the engineers call a pentamode system, because of the 6 elastic modes that you can have in 3 dimensions, 5 of them are soft and would vanish altogether if there were no bending restoring force there. However, the whole lattice resists isotropic compression under pressure. And you can see you can play frivolous games here, and some of the frivolous games are relevant to what we want to talk about today. So here are the what I call Maxwell lattices. Some people would call these lattices, they are well, but let's call them Maxwell lattices for now. You have where the number of neighbors is equal to twice the dimensionality. The word I was after is isostatic. So physicists tend to say that any system in which the number of degrees of freedom equals the number of constraints, they refer to as isostatic. The engineers have a somewhat more complex definition, but you could, if you wish, call these isostatic. So here we have structures where each site has 4 neighbors, and you have each site has 2 degrees of freedom, and each bond is 1 constraint. So you can see that if we have, on average, 2 bonds per site, which is what you have if the number of neighbors is twice the dimensionality, then under periodic boundary conditions, at least, all of these lattices fall into the Maxwell lattice category. That's what my definition of the Maxwell lattice is. So the simplest one, of course, is the square lattice. You can shear the square lattice and you can distort it in a manner like this. And each of these operations leads to a different phonon spectrum and different surface modes in particular. Here you have a very interesting transition in the Kagamine lattice, where you can rotate the triangles relative to each other in a uniform fashion. And that idea can be extended to pyrochlore lattices in 3 dimensions, such as shown here. This is the perfect pyrochlore lattice. Each red site has 3 degrees of freedom, and there are 6 bonds coming out. The 3 bonds on a tetrahedron. And then you can distort this. You can change the lengths and so forth. Nature doesn't do that for you, but you can construct an object like this in 3D printing or various other mechanisms. And when you go from here to here, the topological properties of the phonon spectrum actually change. So I just want to show you now one of the very amusing things that happen in a Tinker Toy model of a topological lattice. So this was prepared by Zeb Rocklin, Shenggang Zhu, Kai Sun, and Xiaoming Mao at the University of Michigan. There's Xiaoming Mao, who was my postdoc for several years. So here I'm going to start this and watch what happens. Okay. Notice this now is a Kagamine lattice that's been constructed so that you can't quite see it, but there are straight lines. Here he's pushing on one side. Notice the surface invaginates very locally, which means that if we look in momentum space, there are lots of degrees of freedom here that are costing no energy. The same is true on the other side. But he's going to distort the system now and undergo a phase transition, not a phase transition, at least a transition, where he goes through a region where there is resistance to compression. So let them finish doing this. Okay, see this line he's drawn? Actually, this system can resist compression along those lines. So you've gone from an original state in which there were no straight lines that resisted the compression, to a state on both sides, different states on both sides, where you don't have that benefit. So both of these are true Maxwell lattices. Now he's going to push on this side. Now watch what happens. It doesn't invaginate. You don't push in a little hole there. You actually move the whole sample, meaning that this side has become very rigid. And now he's going to go and see what happens to the other side. He pushes on it, and you get sort of a point-like depression or invagination, and you just can keep on going, keep on going. This edge stays straight, and he doesn't exert enough force here that he actually moves the sample when he pushes on this end. So that's going to be one of the big characteristics we'd like to understand about these materials. So I should be able to go to the next one. Okay, so here, this is this pyrochlore lattice I showed you earlier. Olaf Stengel and I invented it because we wanted something that had the 6-fold coordination, but was not a simple pyrochlore lattice. So what we found was all kinds of interesting zero modes I'll mention this a little bit later on, but basically there are lines in reciprocal space where you have zero energy modes. So this thing has the property that if you cut it along the right faces, you have a soft part and a rigid part. So they did an experiment where you push down on the two surfaces and measured the load, which is basically the force at a point we're talking about, as a function of the depth of the indentation in millimeters. And the purple curves here are taken, data points taken on the purple part, the top, and the orange ones are taken on the orange base. And notice that it takes a greater load for the same indentation on the rigid side than it takes to do the same impression on the soft top side. So this gives you an idea that you have taken this structure right here, which was 3D printed with two different polymers, one polymer which is very rigid, the gray part right here, and the other part which consists of the nodes, a very soft polymer that is very malleable and reduces the forces required to make rotations, relative rotations of the rods. And this is a picture of what it is. This is at the 10 micron scale. One of the interesting features of these materials is that you can cut it in half or into two parts, and the top part at the top of the new sections will have the same soft property that the original crystal had or block there. So you can say then maybe this could be useful to maybe football helmets, or if you want something that retains its softness as it's damaged with friction or something, you can have it so it works. It has a soft surface for the entire time until you get down to very thin slide. Okay, so a few preliminaries. I really don't know what my audience is here, so some of the language we'll be using. Mostly I'll be looking at ball and spring lattices in d dimensions with n sites and nb bonds. So each site has dn degrees of freedom, and each bond gives one constraint to the problem if it doesn't distort at all. We will be interested in the dynamics of these systems. So there is an equation of motion in the long wavelength or elastic. Well, and this is true for periodic structures because I'm looking at I'm Fourier transforming. So we have basically the acceleration is equal to a matrix times a displacement to give us a spring-like force. And from this, we get elementary excitations whose frequency is omega of q, where q is a wave number, and omega of q is this equal to this dynamical matrix. Now, doing this produces a spectrum of excitations. They're basically the phonons in the system. And the lattices we will look at have many different types of band structure. They have acoustic modes whose energy vanishes at the center of the Brillouin zone, or frequency vanishes. We have optical modes that have gaps between the optical modes and the underlying acoustic modes. What I'm showing here, the dashed lines correspond to a pure Kagamine lattice, and there is a line of zero modes that run down from gamma to the point M in the Brillouin zone. Here is a plot of the full phonon spectrum as a function of QX and QY, and you can see you have these straight lines of zeros that come to the base in a V-shaped structure. And there's a zero mode that goes all along each of the gamma to M. Now, if I turn on a next nearest neighbor force, then you get this other pattern in which the zero mode has disappeared altogether, and I have only the two red lines right here, which are the two phonon modes, acoustic phonon modes hitting zero at gamma. And then up here, I have band gaps of various kinds. Now, the same thing happens when I think I'll go back here just quickly. Oops. So what I'm talking about is going from this lattice to this lattice. In the process, this lattice has the zero mode that runs from gamma to M, and this lattice loses that altogether. It's fully gapped. And, if you just look at the straight green and blue and red lines here, the spectrum of this lattice, when I've turned on the next nearest named forces, is qualitatively very similar to what happens when I twist the Kagamine lattice through an angle alpha. And a particular interest is what happens if I look along this line. Let's put on our glasses and look inward towards here. So what I'm looking at is the K to M line right here, and we're looking at it coming this way. Before we twist it, we have this knife edge that looks like this. Now, some of you may know the Schrieffer-Heeger model and what goes on in graphene at the particular point. This is what you see in those lattices before they do anything to them. When you turn on the twist, then you get a gap like this. And what happens is you get a series of systems for each value of Q, which acts a little bit like the Schrieffer-Heeger model, for those of you who know about that. Now, we're also going to be interested in the elastic limit. That's the limit where you're at long wavelength, and the gradient of the displacement, so that the symmetrized linearized strain is the derivative with respect to position I of the jth component of the displacement, plus the part interchange of the I and J to get a symmetric linear tensor. So in the linear form, the elastic energy, oops, I see I forgot to add something here. This should be a Uij UKL. I left that out. So KIJKL is the fourth rank elastic matrix, and we will see some of the properties that the topological lattices have, or that the elastic tensor of the topological lattices have. You can get the long wavelength phonon spectrum by basically taking the small q limit of this. Then we have, again, acceleration is equal to a force, which is KIJKL times grad. This should be grad K, grad L. I made this one up quickly the other night, grad K, grad L. And here's the elastic tensor in the for an isotropic solid. There's a bulk modulus, which is proportional to the unit tensor delta Ij times delta KL, and then the shear modulus mu, where this whole quantity has, if I take the trace of this, or if I set, if I trace over KL or trace over Ij, I get 0, meaning that we don't have any overlap with the compressional parts of the system. So what are the properties of these Maxwell lattices? Review them before we go to the details. They have a phonon spectrum that has gapped and bulk phonons. They have zero modes at the free surfaces, unlike the Rayleigh waves that you normally get. The topological properties of the bulk phonon spectrum determine the number of zero modes. In other words, these are distortions that occur at zero energy, at specific free surfaces and buried domain walls. The topological change that moves zero modes from one free surface to the opposite one, creating rigid and super soft opposing surfaces. There are nonlinear elastic modes of zero energy, and you can see that in a way here. If we go back to this, here there's clearly a distortion that takes me from the original Kagamine lattice to a twisted one, and in the process, none of the bonds change any length. Now, once I get to here, I can continue to compress it. So all through this spectrum, there is a mode which costs no energy, that is macroscopic in the sense that I can squeeze it together. And then, of course, if you go to more complex structures, like the square lattice I showed you, where you had a unit cell with 4 sites per unit cell, and twist it a little bit, you get these vial modes, which are zero modes in the bulk that move around inside as you distort the system as a function of wave number. So what I'm going to do first is to talk about some mathematical preliminaries, the Maxwell-Calidyne index theorem, which allows you to obtain a relationship between the number of zero modes and something called a state of self-stress, and the number of degrees of freedom and the number of constraints. That's the Maxwell-Calidyne index theorem. Bulk modes in non-topological Kagamine lattices and twisted Kagamine lattices, so we'll talk about those again. We'll apply the Maxwell-Calidyne count to surface modes. And curiously enough, the engineering community who's known this theorem for at least 60 years never looked at the surface modes. Then we're going to look at topological lattices. What kind of distortions do I have to make on the Kagamine lattice, for example, to come up with a lattice that has different number of zero modes on the two opposite surfaces? And then we'll talk about these modes at free edges and at domain walls. And then if there's time, we'll talk a little bit about 3D system, file points and lines, maybe random lattices, probably not, and possibly guessed modes. For those of you who are looking, the first paper about this was by Charlie Kane and me in 2014. And here are two review articles that contain a lot of what I'm saying. Okay, so let's look at some frames that have dn degrees of freedom and nc constraints. For the Maxwell lattice itself, the number of constraints is equal to the number of bonds, which is equal to Zn over 2. Right, basically. So Maxwell says the number of zero modes is dn minus the number of constraints, implying that the number of neighbors per atom, in order to reach this, the Maxwell limit where dn minus nc is 0, has to be twice the dimensionality. These don't have quite that, but they still illustrate the answer. So look at this frame right here that has, there should be a red dot right there, that has 6 sites and 7 bonds. So if we have Maxwell, he says the number of zero modes should be twice the number of sites, we're in 2 dimensions, minus the number of bonds, which gives us 5, and 5 is equal to 3 plus 2. 3, that's the number of trivial rigid translations and rotations that any unconstrained object is going to have in 2 dimensions. And then there are 2 extra modes that cost 0 energy. One is to simply shear the top square. So as I move this from this point, this configuration down to the sheared one, no bond changes length, and therefore there's no force that's been exerted. I can also rotate this triangle back and forth because we're assuming there are no rotational restoring forces here, and that gives us 2 modes. I can now come along and increase the number of constraints. Let me put a bar across here. So now I still have 6 sites, but I have 8 constraints. So according to Maxwell, the number of zero modes is 6 times 2 minus 8, which is 4, or 3 plus 1. So we still have the 3 trivial modes, and we still have 1 mode that here we still have a mode, which is the shear of this. It's the same operation as that, only up and down, but there's an extra bond there. Now let's add 1 more bond. When I do that, we now have 9 bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that says we have exactly 3 zero modes. So this would be, in the engineering language, this is an isostatic structure. But when I added the bond, I added it in a place to rigidify this floppy square, but I could also have added the bond over here without changing the total number of constraints of the system. But now we have a zero mode, which is what this one is. Just by adding an extra bond across here does not affect the zero modes that don't exist in this one. And we have a new phenomena that occurs. This one, if we try to put tensions and compressions and stretching in the bonds, we can't do that such that all of the sites have 0 force. When we have this structure, then we can have that the total force pushing outward is the vector sum of these 2 vectors. Can you see the arrow when I move it up and down? Probably not.
Yeah, we see it.
See, you can see the arrows. And then along the diagonal, you have the diagonal under compression. It pushes outward, and we have a system where we have a stable system where we have tensions and distortions in the bonds, but no forces on the sites. And this is what Calidyne called states of self-stress. They can exist in fact, they do exist in many random systems, even when you have zero external stresses on them. The total number of forces is zero. So what Calidyne says is, yes, I have n is equal to 6 and nc is equal to 9, so that we just balance the Maxwell relation. But we have another phenomena. We have one new structure that can support the self-stress. And so we have n naught is equal to 3 plus is the number of degrees of freedoms plus the number of states of self-stress. And he modifies Maxwell by saying that the number of zero modes minus the number of states of self-stress is equal to dn minus the number of constraints. And that's a general relationship valid for the infinitesimal distortions that we're talking about, right? So this is a linearized theory at this point. Okay, so I think most of you have taken a linear algebra course, though if you're like me, you forgot it all until you had to use it. But we are going to use a lot of linear algebra. So let me introduce some of the notation we're going to use. This U is a dn dimensional displacement vector. So it's a vector that encompasses all the displacements of all the lattice points that we have. F is the dn dimensional force vector. So this is a vector gives you all of the forces on all of the sites. And this should be the forces that self forces, in other words, the force that neighboring sites exert on each other, but doesn't include the external forces. E is the set of all bond stretches. So since there are NB bonds, we have an NB dimensional vector. T are the sets of stresses on the bond. So each bond can be stressed, either stretched so that T is positive or compressed so that T is negative. And we have that. Now, we know that the set of displacements of the lattice are going to have an effect on the strains in the lattice, on the stretching of. So there's a one-to-one relation. Well, I mean, there is a linear relation between the displacements U and the extensions of the bonds C. And this NB by dn matrix is called in the engineering literature the compatibility matrix. We also have another matrix that gives a linear relationship between the tension in the bonds and the forces at the sites. So QT is equal to F, and Q is a dn cross NB dimensional matrix. So now we use a theorem from linear algebra, namely, let's go for it first. The null space of C, in other words, the set of vectors U that are zero under the operation of C, is called the null space or the kernel of C. The null space of Q, or the kernel of Q, is the set of tensions such that Q acting on those tensions gives zero. So that means the null space is the set of tensions such as that I showed on the square lattice back there, such that QT is zero. So N0 is what's called, it's the dimension, the algebra dimension of the kernel of C, and S is the dimension of the kernel of Q. So the rank is basically the dimension of the space where things actually happen. So the rank of C plus N0 is dn. That's a theorem. The rank of Q plus S is equal to NB. And there's a theorem that says the rank of C is equal to the rank of Q. So from that, we can subtract these two things because the two ranks are equal, and we get the Calidyne, the Maxwell-Calidyne theorem that the number of zero modes minus the number of states of stress is rigorously dn minus nb. Incidentally, that dynamical matrix I referred to earlier can be written as a matrix of k's. In this case, I just made it a scalar of C dagger C, and you can prove that C dagger is equal to Q, so C dagger C is equal to Q dagger. In a sense, C or D is a kind of square root of the dynamical matrix. Now, the nice thing about a periodic system is that you can diagonalize the displacements and their energies and force we're using a Fourier transform. So for all q not equal to 0, we have separate vectors whose dimension is, we have the number, excuse me. We have the number of zero modes at wave number q minus the number of zero modes at wave number, as a self-stress at wave number q is equal to the dimension times the number of sites in the unit cell minus the number of bonds in the unit cell. So let's see, I got to move this so I can see it there, right? I'll move you down here. So N0 of Q is the number of zero modes at Q, and S of Q is the number of states of self-stress of Q. For a Maxwell periodic lattice, so this is one where we go to periodic boundary conditions, so there are no edges. Then we have Dn is exactly equal to Nd, that's the number of bonds per unit cell, and N0 of Q for every Q is equal to S of Q in the bulk phonon spectrum. So there's exactly one zero mode for each state of self-stress, which will not be the case when we introduce edges. What's going on now? Okay, so we've basically done this. Let's just go over it quickly again. This is the Kagamine lattice, and notice, except for some region here where I've shown what the zero energy distortion is, has straight lines of bonds that go all the way across the sample, and you can think of this as being wrapped on a torus. It's wrapped on a torus, and that means that this end of the straight line, which is a straight line of bonds, is connected to that end. So that means that you can put this under stress, say, imagine blowing up the torus, stretching out the bonds, and what you will get is that you can have stress in every one of these bonds going along there without having stress in the other ones. So basically, we have a number of bonds which is proportional to the perimeter of the system, bonds going across there. So each of these straight lines has a state of self-stress and therefore a zero mode. And the zero mode is each mode along this knife edge that we looked at earlier as a function of Q running along there. So here are the zero modes going this way, and their origin are these straight lines, states of self-stress. Now, when I twist it, the system like this, we lose all of the straight lines. So that means that we no longer have any of these straight line zero modes. The Q equals 0 is slightly different, but mostly it's still true that what we're saying is true. So as I change alpha, I don't change the qualitative features of the band structure. So that means that we have a topological class which is robust as I compress the system like this. And we have the zero modes in this behavior right here at the edge. This incidentally defines a length scale for you. Q star is the length at which this thing sort of, you can take it to be the point at which it curves over, and you can create an omega there where C is the sound velocity. Now this is the full guessed mode I was telling you about. You can go all the way down to this, and we will have something more maybe to say about this later. Okay, now what happens when we change the torus into a strip? In other words, we have the torus, we take a knife, and we come along and we cut all the way around the torus and then spread it out. And what we get is a ribbon, right? A ribbon which looks something like this. To get this ribbon, look at here. Here I have a triangle coming off, and then an inverted triangle going the other way. So if I cut along here, I separate the top part from the bottom part, which then tells me that the bottom part looks like this and the top part looks like this. And what has happened then? I have removed 2 bonds per unit cell. So we have, and since I've broken the contact between this point and the opposite point in the end, I've destroyed the efficacy of this straight line to be able to support self-stress. So we've removed 2 bonds per unit cell, and we have removed in the process 2 states of self-stress, the ones that go like that. So that tells us that the change in the number of bonds is equal to the change in the number of states of self-stress. So this is the Maxwell-Calidyne relation for the new system. The new N0 minus the new state of self-stress is equal to dN minus NB prime. And NB prime is NB minus delta NB, so that N0 prime minus S prime is equal to delta NB. But S prime is equal to S minus delta NP. So we immediately get that N0 prime is equal to S is equal to the original, because S is equal to N0. You have the same number of zero modes as the periodic boundary condition gave us. But what happens when we twist things? We no longer, we still have removed 2 bonds per unit cell, but we've lost the states of self-stress. So now S prime is equal to 0. And when you go through the algebra here, N0 prime is just equal to delta NB, the number of bonds that have been cut per unit cell on the surface. So that means that we necessarily now have 2 extra two zero modes on the surface per unit cell coming from that. Now, we don't know which side they're on for a standard lattice. But let me just say something about the zero mode that comes out of this lattice. It turns out that you have the same properties on both sides. They're symmetric. And you can look at a, excuse me, my mouth is dry here. Let's take, let me interchange QX and QY here, because over here I have them backwards. If we look at the penetration depth of a zero mode, in other words, the U on the surface dies off with displacement Y in this, no, this is correct. Displacement Y in this direction, and it oscillates. This should be a Q. No, it's backwards. I'm sorry. So on the picture, this is a Y and that's an X. And then it's periodic along the surface X. And you can see that we get a length scale, which is the inverse of this QY. Well, this is the one that's wrong. Yeah, I apologize for that. Yeah, when QY goes to infinity, this goes to a 1 over L. And when it goes to 0, it goes down to 0. So in any event, we have this curve then is showing the penetration depth as a function of the amount of twist that we've done, the twisting angle alpha. And these, all of these lines asymptote to this straight dotted line, which is exactly what you can find if you look at Landau and Lifshitz mechanics. It calculates the surface Rayleigh wave, and it has exactly this form for its energy if you have a system with 0 bulk modulus. And we told you that these twisted, that these are for the twisted lattice, and that we have exactly the same long wavelength sound or surface velocity as calculated directly from the elastic theory. Okay, so now we're going to get finally to topological things. So here is the twisted Kagamine lattice, which we're going to call a non-topological lattice for reasons which will become apparent in a minute. Now we need to have some way of changing the topology, the characters of it, the properties. Now what we saw before is that if I twist all of the directions, and I twist this back to a Kagamine lattice, we have straight lines going in all 3 symmetry directions. So we're going to simplify things so that we rotate these so we get a straight line of bonds along one direction only. So here is a critical point that separates this the non-topological lattice from this, the topological lattice. So there are complicated formulae that tell you how you twist these things so that you preserve straight lines and so forth. Basically, you distort the lattice along directions P and A. A is the direction of the unit cell directions, and P basically are the directions of the conjugate reciprocal lattice vectors. And so you have this formula. When you apply it, then we go from here to here, and we keep the sum of these x's right here, the x mu, x1 plus x2 plus x3 equals 1, and you get in that operation, you have a phase diagram expressed in the x1, x2, x3 plane, where the center is what we call the twisted Kagamine lattice. It has no polarization. This lattice has a polarization RT, which I'll discuss in a moment, but basically in each of these three different directions, the blue arrow is telling you the direction of the of a polarization vector, which is analogous to what you see in the Schrieffer-Heeger model, and it points typically from here to here, from that. So here's where we come in. The number of surface modes on a surface characterized by a reciprocal lattice vector G. You recall the reciprocal lattice vector G, when it's perpendicular to a lattice plane, when it's coming to a lattice plane, points perpendicular to the line of the lattice plane and has a length scale between neighboring straight lines of bonds, which is given by this formula here, where B is the length along this direction. So here, this is a function of the vector Q. I've broken up into Q, a unitless, a scalar that's telling me direction along the lattice plane, and P, we're going to we're going to change the P to a variable exponential of 2 pi IP over G, and ZQ is 2 pi IQ over GQ, so that what we're going to do is to fix ZQ, that's this guy, and allow Z, that's this guy, to vary. And then we're going to do a contour integral of the log of the determinant. This is what gives us the information about the topological properties. Notice that this is the log of a determinant, so it's by its nature unitless. And this guy, the dz, d by dz is unitless. So this over here is a number that is unitless. And what you can, spend more time than I have, you can show that this number is equal to the reciprocal lattice vector G dotted into RL plus RT. Now, you can see that there are many different ways you can define the unit cell. And so what we're going to call RT is not gauge invariant. This is, you take some reference unit cell, like this one or this one. These are different unit cells, but they have exactly the same physics. And then when you look at the surface, there is a vector that's telling you something about how the surface unit cell differs from this one, and you take the product and you get then the number of surface modes at wave number Q along the surface for a lattice plane that's characterized by the reciprocal lattice vector G. So the only thing that we have left to do is to show RL. Well, let's look at this unit cell labeled 1. So this is a nice symmetric unit cell. But when I go to the surface, if I try to use this unit cell, I have dangling bonds that stick out the edge. You don't want to do that. So what you want to do is to redefine the unit cell so that it lies completely within the material and doesn't have anything sticking out the edge. So here at the top, we have something that we've cut the two bonds like this, leaving behind these exposed triangles. And in the process, we've cut two bonds, and our surface unit cell is, you can take it to be this thing, for example. I didn't draw this one in red, but it's an image of this one, or it can be this guy. Doesn't matter. You can choose whichever one you want. And then what you ask is, what bonds do I have to move in order to make this one look like that one? And RL is twice the distance to sum over all of the sites in the unit cell of the position of sites that are moved to go from here to here, minus the sum over the bonds. So for example, if I look at let's see, which is the cleanest one here to look at. If I look at this one going to this one, the only one that's different is this guy right here is equivalent to that guy, but I've moved him from here up to here, which is a lattice spacing along minus a, let's see, did I? Yeah, here we go. This is A1, A2, and A3. So the direction that we had to displace that bond is minus A3. So the net result is we know how to calculate RL, we know how to calculate RT for the reference state, and then we can find that in fact that RT is equal to, well, you know what RT is, you know what RL is, you know what G is, and we can calculate the number of the number of zero modes. So here's the first one is interesting. We had to move 4 bonds to go from, no, I should have had this one here. Well, to go from the original to here. And that means that I have 4 zero modes and a unit cell which has lost, it has, the surface unit cell is bigger than the unit cell in the interior, and it has 4 sites, 1, 2, 3, 4, I think, right? And then the next one has 1, 2, 3, 4. It has more sites than the bulk does. And so you can carry out this calculation and you get that there are 4 modes, and this shows the penetration depth as a function of a vector along the surface. And this one right here is degenerate, but I really do have 4 different modes. When I go to this one, then I have moved 3 modes, 3 vectors, 3 bonds actually in this site, and the n becomes 3 instead of 4. So on one surface I have 3 guys, and the other surface I have 1 guy. And then we have the one that's much more like the original, where we have two which can be, in this case, 2 on one side and none on the other side. So that does most of what we wanted. Okay, so just to cover, a couple of other things that happen. This shows us a lattice that has the Weil modes, and you can see here in the density. So this is in color or darkness intensity. It gives you the closer you get to 0, the darker the intensity is. So these are 2 zero modes, and you have the acoustic phonons coming in like this, and they have a peculiar property that their frequency goes as q squared near the origin there. Here is the model I showed you where the experiment was done with the invagination. It has, here is its Brill-1 zone, and you can see these lines. These lines all have 0 energy, and yeah, so, and they do the same thing in all of the directions. If you look at, you can look at jammed lattices. Well, let's just do one more thing here. I think I won't cover the random stuff right now. I think it's probably more interesting to make one more statement. My time is about 2 minutes from being done. The Maxwell lattices have some exotic elasticity. So the Kagamine lattice has all of the elastic constants that a standard isotropic elastic medium has. The epsilon ij are the linearized strains. And here we take, for the nearest neighbor bonds, we have lambda equals mu is 3/16 k. When we go to the twisted lattice, we found we had this guest mode where you can compress things isotropically. So here, looking at this, you can clearly see that there are two zero modes in the elastic energy, one in which epsilon xx is equal to epsilon yy, and one in which, it's one in which epsilon xx equals epsilon y and epsilon xy is equal to 0. You need all of those things to give us a zero mode, which is basically the guest mode. So you can see that this would say that the Poisson ratio, which is the ratio of the compression to the stretch if you take a rod and you pull on it, stretch it out, normally you expect the rod to compress in the direction perpendicular to the pull, but the twisted Kagamine lattice has the opposite behavior. When you pull on it, it increases in size. And one comment here, this I don't expect you to digest completely, but you can ask yourself, how many surface zero modes do I have? And, can I see that analytically? Well, each strain has d times d plus 1 over 2 independent components. So the elastic energy can be written as 1/2 epsilon A, KAB, epsilon B, where this A runs over 1 through 6. That's called the Voigt notation. So it shows that in order to have a completely stable long wavelength elasticity, I have to make sure that the K constants in KAB, KAB can be diagonalized, and when it's diagonalized, you have wave functions epsilon lambda, and since it's in 3 dimensions, it's a 3x3 matrix. We have to have 3 positive constants, and in the 3 dimensions, we have to have 6 positive ones. So under what circumstances do you not have that? Well, if one of the eigenvalues is 0, then we have just 2 Ks, and we have a zero mode that goes along with that. And it turns out that the expression for the elastic energy is really quite amazing. An affine transformation is one where you set a new position R prime of site R equal to a matrix, constant matrix lambda times R for every R in the sample. That's an affine transformation, and your usual long wavelength elastic energy is in fact for an affine transformation. And what the energy actually is, if I have just a single elastic constant, is it's E affine dotted into the orthonormal basis for the Q equals 0 states of self-stress, and you can prove all of that if you wish. Okay, I think I will stop there. It's exactly 3 o'clock. I should be able to return in person here, and maybe we can figure out how to have questions if you're still not asleep.
Thank you very much. We thank Tom.
Yeah. Right.
Thank you very much.
I have no idea how many people are listening. How many people are listening?
Here, let me see. Well, most of the people is in YouTube, so I don't know. Maybe someone can tell us how many people do.
Oh, they usually tell you how many people are.
Here we have 24, but most of the people is not here. It's in YouTube. There's a YouTube.
Oh, I see. They're on YouTube. Yeah. Okay, that's interesting.
So here we have,
yeah.
So if there are some questions, we're open to have any questions. And maybe someone can tell me if there are any questions in the YouTube channels. If there are no questions in the chat, no, there are no questions for the moment. In YouTube, you don't have. Okay, so I'm going to ask you a question. First of all, thank you very much. This is a very nice talk. It will take some time to digest it. But yes, my question is concerning my question is concerning when you, for example, talk about, for example, topological properties in electronic systems. Usually they are robust to disorder. So you look at global symmetries. So for example, time reversal, or it breaks time reversal. So is this the case for this kind of system, or when you add disorders, very different?
So unfortunately, it doesn't depend on the global symmetry. Essentially, all these lattices had P1 symmetry.
Mm-hmm.
Let's see, do I have a picture of that somewhere? I think I don't. No, I don't. I'm not sure I can hunt that down, but it's if you look at this, even these three lattices. I've forgotten exactly what goes on. My recollection is that these are actually this one has a higher symmetry than these two, but I think these two have the same macroscopic symmetry. In other words, they both have a. I'm sorry. This is a bad example. I need to show you two different topological lattices. Let me see if I can find that one. No, I don't have a good one of the two. Well, yeah. So anyhow, the answer is that if you look at it carefully, that there are many examples of lattices having the same symmetry but different topological properties. So this is different from the Landau-Ginzburg paradigm, where everything is determined by symmetry. But what it is you have a group that has to do with how the band structure changes.
Mm-hmm.
And this is a particularly simple kind because for each value of Q, you have basically a mini Suschreiber-Heeger model.
Mm-hmm.
And yeah, I mean, and the Suschreiber-Heeger model has basically two states.
Mm-hmm.
And each of the lines of self-stress that then can be distorted one way or the other. Gee, do I have a, I might. Yeah, I do have it somewhere, but it'll probably take me, a couple of minutes to track it down. So I don't have, clean algebraic proofs with me, but you can certainly look at the symmetry and see that there are lots. I mean, if you look at these things, this doesn't have this hexagon, doesn't have any symmetry to it at all, really.
Mm-hmm. So,
it's if you try to rotate it by 2π/6, you don't get anything out of it. The same is true of this one. Now, this one has a symmetry going down the line, but I could easily have distorted this a little bit. So this point comes down to here, and that won't change the topological class. Because in order to change a topological class, I have to go through some state that is a transition state. Okay. So if you know the Suschreiber-Heeger model?
Yeah.
Yeah. So there you have a line, a double bond, a single bond, a double bond. Or you can do it the other way. So how do you get from one state to the other than translating it and redefining what it is you go to a state where you have both of them hybridized bonds of some kind, so they are identical.
Yeah, exactly.
And so you need to do the same thing here. And it's clear for the example we have here that no, let's see, which one do I want to look at? Yeah, so look at these. This state is an intermediate state. It has these states of self-stress, which dump the zero modes back into the bulk.
Okay.
And now, if I came along and distorted these a little bit and moved it over to here, etc., I wouldn't change that much. Now, of course, the model, this thing, it has the property that just by shearing it, you go through one of these states where you have a straight line of bonds. Well, in this case, the geometry of the Tinker Toys is a little confusing, but it's set up so that there is a line that can support the state of self-stress running around there when he crosses the point that takes you from one to the other.
Okay.
Yeah.
Okay.
If I remember, I'll see if I can find a paper that talks about that.
Thank you.
Yeah.
Yeah, that will be very interesting. We have time just for another question. There's a question in YouTube. Could you explain what is the connection between the dynamical matrix and supersymmetry? If there are any.
Well, okay, so you can write the, normally we're used to looking at Q, rather looking at energies for phonons in a periodic lattice as the dynamical matrix is equal to C dagger C or D dagger. Yeah, right. And that's all you need for standard calculations. Now, what we did with Charlie was in asking about what happens when you go to topological, then rather than having a 2dn by 2dn matrix, excuse me, if I look at C dagger C, right, then the C matrices are dn by nd, and right, and so the C dagger C is a dn by dn matrix, which it has to be because U has dn components. But now I can make I can expand the thing and have in the upper right hand corner I can have C dagger C, and in the lower corner I can have Q dagger. And of course there are complex conjugates of in reciprocal space, they're complex conjugates of each other. And so now you have something where I can write the whole thing. I start off with a n plus dn plus nb matrix. Well, actually, we're talking about the Maxwell lattices. So I have a matrix which is 2dn by 2dn with just C in the upper right-hand corner and Q dagger, I guess it is, in the lower right-hand corner. And then I multiply the two together and I get the full supersymmetric lattice thing. So it's a bit of, it's mathematical trickery, but doesn't, and I should say, right, okay. I have to say that supersymmetry is not something I have looked at in the last 20 years. So it's also true that the supersymmetry has the Maxwell-Calidyne relation built into it. So you have a psi and you have a fermion and a boson, and you ask what kind of modes you have in it, and you have a formula which takes the boson number and the fermion number and relates them to properties of the Hamiltonian.
Yeah.
So I hope that's an answer.
No, thank you very much. In fact, for us, it's very interesting because we are working with flat bands in graphene, and you can make this kind of transformation. So I was wondering if there is some connection between this flat band that appears in twisted graphene layers and this.
Is there a relationship between a supersymmetric model and this? The reason for the flat band in our case has to do with the fact that you are at a critical line separating the two different topological classes. That's what the lines of straight. So presumably there's a possibility of doing that in any of the supersymmetry things.
Okay.
I mean, there's some underlying Hamiltonian that you can jiggle so that, yeah. you must have an interplay between the bosons and the fermions in some way there.
Okay.
Yeah. Okay. Well, I'm sorry this wasn't face to face. We could have gone out
Yeah.
and had a nice bebida.
Bueno,
It's
next
all
time
over.
we're going to invite you to Mexico. So the director of the institute asked me to thanks again your participation. It's very important for us having the presence of people like you with such a very big famous.
Well, I have a soft spot in my heart for Mexico, I must say. It's a fascinating place. Yeah. And of course, they speak a language I can get along in.
Yeah, so maybe once in the future you can visit us if you want. We're going to be very happy to have you. So
thank you very much.
So thank you again. We thank again.
Yeah. Okay.
Well, thank you.
Just push the button to shut us off or what? Yeah, I enjoyed giving the talk, even though it's a little bit strange talking to a television screen.
Yeah, we know everyone. But usually we invite the people to come to Mexico and spend a few days, and that's how it works.
Of course. But it's not clear I would have gone yet. I actually turned down, I am giving a series of lectures by Zoom to Sao Paulo because I chickened out going on the airplane. They say everybody my age is a big, much more in danger than others.
Okay, well, so thank you very much again. So
thank you.
Bye.
So you want me? Zoom.
So.
Okay, I'm leaving the meeting unless